Hello, Lucia. How are you? Welcome to the stream. Today we're gonna be solving this problem. Let me pin the message. It's called a prime palindrome, and given an integer n, return the smallest prime palindrome greater than or equal to n. So here we get the definitions of prime, which, as you may know, a prime has exactly two divisors, 1 and itself, and 1 is not a prime number. Here are examples of primes: 2, 3, 5, 7, 11, and 13. And an integer is a palindrome if it reads the same from left to right as it does from right to left. And we get examples, and the test cases are generated so that the answer always exists and is in the range from 2 to 2 times 10 to the 8th inclusive. So here, if n is 13, the output must be 101, and n is up to 10 to the 8th. All right. The acceptance rate is 26%. It's kind of low. It's a medium. Problems which this pattern the next of some kind of numbers. So you're getting a number n, and you need to return the next number that has some property. In this case, the property is being a prime and a palindrome. So the simplest strategy to do this is to just try it. So just test the condition. So the code would be, if we do the simplest strategy, would be to just, is it a palindrome? So if it is not, we increment it, and we finally return n, right? So this is probably too slow because the numbers are up to 10 to the 8, but the actual worst case depends on how big the gaps between these numbers can be, right? Because we could have to go over all the numbers of the biggest gap, but we don't know how big that gap is. Probably there aren't many numbers of this kind, so the gaps could be big, but let's try it out. And then if we get a TLE, we can optimize it. Even if we don't get a TLE, we're gonna think about better ways of doing this. So okay, so this is very simply if it is a prime, but let's do the first condition. If it is a palindrome, let's shorten this name. So if it's a palindrome and if it is prime, it is a prime pal. So let's do helper functions. So like it says in the definition, if it reads the same from left to right as it does, so we can reverse it. And if it is the same, and I like to do this numerically. Some people do this by converting into strings, but I like to do this numerically, which is So you can think about numbers, sequences of digits. And so this is the way where we iterate all the digits from least significant to most significant. And this is how so in one sense, we are popping. If you think about, we're removing the rightmost digits, and then we are shifting, and then we are appending it to the result, which is shifting to the left and adding a new digit, and that's going to reverse. And then we want to check if a number is prime, and we can do this quickly if we remember that we only have to test. So by definition, we want to know that it's only divisible by 1 in itself. So if we check in all the numbers from 2 up to the number -1, so n minus 1, and none of them divides n, then it is prime. But one property is that if it's not divisible by, we can go up to the square root of the number, and that's going to make it faster. So on the one hand, we have the special case of 1, which is not a prime. And then, like I said, we want to check from 2, and we want to go up to the square root, which remember not to use the square root function. This is faster to do. This is actually just a multiplication, which is faster than the square root function. And so if n is divisible by d, then it is not a prime, and here it is a prime. If we go over all those candidate divisors, then it is a prime. So this should work. This should work, but might be too slow. Yeah, is pal. All right, so let's see if we get TLE. We're probably gonna get TLE here. Yep. All right, so yeah, and it's not even one of the biggest. Well, like we said, it depends on the gap size. We solved a lot of problems, 51 from out of 61, so we are not far from getting this. Right. Okay, so that was our first attempt. And so an alternative would be, so here we have 2 sets of numbers, the palindromes and the primes. So maybe instead of going over all the numbers and testing, maybe we can generate them quickly. So maybe we can generate the palindromes because we know there are not that many, right? Because notice that if we have so if you have, for example, 1, 2, 3, and then 2, 1, so this already characterizes the number, right? This is, if you have this, you can generate the remaining digits. And the same if you have an even number of digits, then this already characterizes the number. So that means that roughly, so if you have numbers up to 10 to the 8, you're gonna have only the half of the digits changing. So that's 10 to the 4, which is not much. So it seems like this strategy of generating the palindromes should be fast, and then testing the. We can test for primality in the same way that we're doing now. But so to generate the to write the code to generate the palindromes, we can think about it this way. So we have, let's say that we have an odd number of digits. So we're gonna have a middle digit, and then so this is supposed to be the same as this. So like we said, this part right here characterizes the number, and then we just want to get, let's call this n1, this part, and this is n2, and we know that n2, so I'm calling n1 the whole thing, including this digit. So n2 is going to be n1. In this case, we have an odd number of digits. So by dividing by 10, we are integer division. We are essentially removing the middle digit, and then we can let's call R the reverse function. We reverse the digits, and then we get n2. So how do we do that? We can create a function that is going to return all the palindrome numbers. And what do I mean by all? I mean all of them, actually, because of the magic of Python. So let's say that we know the number nd is the number of digits. Initially, it's going to be 1, and so. But let's see what the code would be. So if we imagine that the function is already implemented, and we have a function that is going to return all the palindromes in order. So what we want here is pal to be greater than or equal to m, and is prime. Remember that we always apply the condition that is quicker, so that if it fails, we don't have to check for prime, whether it's a prime. It's just a micro optimization. Well, not so micro in this case. So then we return it. And we know we're guaranteed that we're going to have a result. And then here, so the number of digits of n1, so nd1, let's call it, and then nd2 is going to be the number of digits rounded up. So if we add 1 and divide by 2, it's the half of the digits rounded up, and then the other one is rounded down. So this is going to be the number of digits in each of these parts. So now we want to generate all the numbers that have exactly nd1 digits. So the first one of those numbers is going to be a power of 10 nd1 minus 1, because this is going to be the number of zeros in the number. The minimum number with nd1 digits is a 1 and all zeros. And the number of zeros is nd1 minus 1. And then we want to go up to the next power of 10, exclusive, because that's going to have one more digit. And now we want to yield this number that is going to be nd1, but we want to shift it to the left. How many times? Well, nd2, because we need to leave the space for the n2 part of the number. And like we said here, n2 is going to be so this is n1. It's going to be n1 divided, so we want to divide by 10 to the, and here it's nd1 minus nd2, which is going to be 1 when the number is odd and 0 when the number is even. So that means that we want to cancel the least significant digit only when the number is odd. And then we want the reverse, that we already have that function, luckily. So that is going to give us all the palindromes. And I think we have if express. Oh, well, no, this is right. Oh, we're not incrementing the number of digits. Sorry about that. Yeah. So this should be fast enough, and it is. So more specifically, when we said, so we said that the number of palindromic numbers was around 10 to the 4 if we have up to 10 to the 8 numbers. The numbers are up to 10 to the 8. But yes, notice here that if we have, for example, 1, 2, 3, we can turn that number into 1, 2, 3, 3, 2, 1, or we could turn that number into 1, 2, 3, 2, 1, right? So in this case, we are generating a even digit number palindrome and here an odd palindrome. And notice that if we have this number, there is exactly one way in which we can turn it into this this number. So this means that there is a 1 to 2 correspondence between these numbers and the palindromic numbers. So that means that if we count all the numbers of 4 digits, which are this, but we don't want to count 0, so we subtract 1 and we multiply by 2. This is going to give us all the numbers of up to 8 digits of palindromic numbers. But then we're told that we have to consider numbers up to 2 times 10 to the 8. So that means that we also want numbers which start with a 1, and of course if they are palindromic they have to end with a 1. Here they have 7, so in total they have 7 digits, and therefore the part that characterizes the number is going to have 4 digits. So again, there's going to be 10 to the 4. So if we add 10 to the 4 here, that's going to give us the total number of palindromic numbers that we need to consider, right? And if we count this, just to make sure that we are counting correctly, so the maximum number is 2 times 10 to the 8, as we're being told here. And so if this is greater than the max, we break, and otherwise we count. And we print the count, and let's print what we counted, which was 2 times 10 to the 4 minus 1 plus 10 to the 4. Let's see if those things are the same. And they are. That is exactly so. That's why this works, because there are not that many, 30,000. And cool, yeah. So there's still a few more things to say about this. So yeah, notice that we decided, so we had two tests. So we're finding the intersection of 2 kinds of numbers, palindromes and primes, but we decided to generate the palindrome. So another approach would have been to generate the primes and then test for whether they are palindrome, but there is no way to generate the primes practically, and even so. And another argument that we used to generate the palindromes was that not only they were easy to generate in this way, so remember this way of generating palindromes, because it comes up and I think this is a very compact way of doing it. It comes up many times in LeetCode, but so the other argument that we used was that the density was low. There were not many, so we said that there were a square root of 10 to the 8. But how about the primes? What's the density of the primes? Well, there is one thing that is called the prime counting function in math that tell us how many primes are there up to some number. And here we have a table. So for example, up to 10 to the 8, there are 5 million, almost 6 million primes. So 2 times 10 to the 8, there could be 6 million, so 12 million, 10 million, something like that. So there are more primes than palindromes. So we counted 30,000. So that's another argument for choosing the generation of palindromes, right? So another idea here is that, which you might not be able to tell, but here where we are generating the numbers independently, we're testing, generating, and we're never using any property of the whole the prime palindromes, right? We generate palindromes, we test primes and independently, but it turns out that there is a relationship. So notice that there is a relationship, because if you between the structure of a palindrome and whether it's a prime or not, because remember the divisibility rules. So there is one divisibility rule by 11, which is that you check. So if you have a number that is the 0, so these are the digits of the number, number of n digits, and so when you check the divisibility by 11, you can check the sum of the digits, but the digits with even index are added, and the digits with odd index are subtracted. Okay, so here this is added, this is also, it is subtracted, and so on. And if you apply this this calculation and you get a number that is divisible by 11, then the whole number is divisible by 11. So this is one of those rules that you have to remember. It's similar to the rule of divisibility by 3, where you just add the digits and you check whether the sum is divisible by 3. So you can ask why this is the case, and the proof is always expressing the number as a polynomial. But well, first let me explain why this matters here. Well, notice that if you have a palindrome, so this 0 is going to be the same as the n minus 1, right? Because that's the definition of a palindrome. And if they have a different, if they have a different sign, then they will cancel out, right? So if you have, for example, a number of four digits, right? So this is going to be minus, and then this is going to be plus, and the 3. So notice that this 0 and this 3 are the same because this is a palindrome. So this will cancel out, and the 1 and the 2 are the same. So this will cancel out, and this is going to be 0, which is divisible by 11. So that means that for every number that has an even number of digits and is a palindrome, then it cannot be a prime because it will be divisible by 11. Well, with the exception of 11 itself, right? Because 11 is a prime. But we know that a number, an even digit palindrome is always divisible by 11. And let me refresh why this is why this rule applies. Well, so remember that you can write a number as so the 0 plus the 1 times 10 plus the 2 plus times 10 to the 2 and so on. And here you have the sub n minus 1 times 10 to the n minus 1. But notice that 10 is congruent or is equivalent to minus 1 mod 11. And therefore, you can replace all the 10s with minus 1. And remember that minus 1, so if you have minus 1 to some power, if the exponent is even, then you'll get 1, and if it's odd, you'll get minus 1. So that's how you get this alternating sum that we have here. Okay, so that proves that we only need to care. So let me start sharing my solutions. So this one took 250 milliseconds. And so this is not gonna give. So sometimes when you do optimizations, the design of your code starts so here we assume that these problems were independent. So we separated the generation of palindromes with the testing for whether it's a prime. But now we're going to intertwine because we're only going to generate the palindromes that can be, that are not that we're going to discard some of the. Hey, thanks for the follow. some of the palindromes that we know cannot be primes. So the number of digits are going to be always, hey there, always odd. So we start with 1 and then we add 2, right? But remember that we need to consider 11, right? So that is a problem. 11 is the only exception here. So how do we do that? Well, we can do a hack here. Like if we're starting with the digits of 3, then we yield 11. That's a hack, right? And so this should work. Let's comment that out for now. Okay, so it works and it's faster, 191. That's cool. So this wasn't necessary to solve this problem, but it's interesting to know these rules of, so whenever there is a property involving digits, then you can think about the divisibility rules in terms of digits. But so one question would be, how many are there of these numbers, right? So how many are there in total? So what if we only count the ones that are primes? So how many are we going to get? So our intuition initially was that there were not many, and that's why we got a TLE at the beginning, because there are big gaps. And so there are only 2,200 of these numbers in this range, which is a pretty big range. So that's interesting. So maybe we can, so I'm not sure, so I'm not sure if sometimes I think that LeetCode first runs the same code for 2 divisions. Shouldn't say exactly 4 or exactly 2 positive. Yeah, I think, oh, so this is assuming positive integers. It's not specified, but I think that's the assumption. But yes, you're right that when you talk about integers in general, then you should count -1 and -n as divisors. So what was I saying? So yeah, let's try it. What if we generate them all the palindromes here? So I'm not sure if this is going to make it faster, but it might. So let's check it out. So here we are going to generate all of the numbers that we care about. Well, actually, it says 2 times 10 to the 8, but we don't even care if we have any number that is greater than 10 to the 8, then we are done, right? So this maximum is not really what we care about. So if pal is greater than 10 to the 8, then we don't need anything else. We can break. So yes, it's interesting to know. So this could be less than what we had before. So how many pals do we get, and what is the maximum of them? Let's check this out. Okay, so there are a lot less, only 782. And this is so this range is a lot bigger than it needs to be. Cool. So only 782. So now we can do a binary search, right? So we can. What does the second number mean? What second number? Oh, this one. So yeah, this is the maximum. Oh, so -1 is the last element here in Python. So this is the biggest prime palindrome that we need. The 782nd. Yes, that is correct. That's very precise. Yes, if we so this is 0 base, so if we change this to 781, we should get the same one. You see? But yeah. Okay, so now we can do a binary search, right? Because so bisect left of impulse of n, and we just return that value. So I'm not sure if this is executed once and then all the test cases run this code. In that case, it should be faster than before. So it's not significantly faster, just a little bit. But it was a nice try, I guess. Okay, but I'm surprised that there were, in the end, there were only. So yes, I guess we should have known that there are, that we didn't have to exceed 10 to the 8 too much to get the next prime palindrome. So one way to, so these numbers are pretty well known. So they're called palindromic primes or pal primes. So you can learn more about them here. So here, for example, except for 11, all palindromic primes have an odd number of digits because the divisibility test for 11 tells us that blah blah. So this is what we went over. And it's interesting that it is an open problem whether there are an infinite number. Infinitely many palindromic primes. So this is the largest known palindromic prime. So notice that these numbers are not really significant in the sense that they depend on the base 10, which is pretty. So this is the convention that we use to express numbers, but it's pretty arbitrary. You can, if you ask for whether they are palindromic in a different base, you'll get different numbers. So that's why it's not really something important mathematically. But it is well known. Some people have asked this question before. And so one thing to notice, so here we are given the sequence in this site, which is called the Online Encyclopedia of Integer Sequences. So sequences have a code in this site, in this encyclopedia. And this is a good tool to have because here we knew how to find this sequence because of the name, palindromic prime or prime palindrome, etc., pal prime. But sometimes you have a sequence and you don't know what the name is, or there is no name, so you can search it by the by numbers in the sequence. So here, if we get these numbers, so let's go to the main page and we search for the numbers, and we immediately get the palindromic primes, right? So I chose up to this number. So this number is obviously important here, otherwise we'll only get the first 5 primes. But once you give it this number as well, you'll get a lot of information about the sequence. So this is a good resource for problem solving. I have it somewhere here, I think. Yeah, here. So it's good to have it. So I'm gonna share it. It's good to know it. So and also looking in Wikipedia, it's a fine resource for understanding. Okay, so that's all I have for this problem. So thanks for watching and see you on the next one. Bye bye.